Hi grade 11s and welcome to this video. In this video, we will be working on the Mathematics Paper 2 for June 2023. Okay, so this paper is specifically from the Gauteng province and we have a time of 2 hours and it's worth 100 marks. Looking at the instructions, this paper consists of 8 questions. If necessary, round off to 2 decimal places, okay? And also just remember that the diagrams are not necessarily drawn to scale. Okay, with that being said, let's get into this video. Question 1 says, the following box and whisker plot and accompanying 5-number summary shows the marks obtained by grade 11A for a mathematics test out of 50. The 5-number summary of grade 11A is, and they give us the 5-number summary and also the box and whisker. So we can always just see what exactly the minimum is, or for example, like Q2, okay, it's actually 21, and so on. And then they tell us that the following data shows the marks obtained by the learners in another class, grade 11B, for the same mathematics test out of 50. Okay, and the first question is to determine the 5-number summary. Okay, there should be 4. So for grade 11B. Okay, and I have just filled in the ones that were missing. Okay, there was a exemplar watermark. Okay, so that is gone now, but it also took away some words here and there. Okay, so this is what we have. 1.1. We have to determine this 5-number summary, but this clearly seems like it's already in ascending order. So let's go ahead and find this. How many numbers do we have first? So with this, we can easily see that the minimum value is 10 and the maximum value is 48. We just need to find the Q's, okay, the quartiles. So Q1, and Q2, and Q3. It is easier to find Q2 first, because it's the middle, okay, the exact middle. So to easily find this, instead of counting how many numbers you have, you can with a pencil lightly scratch out. So first and last, second last, third and third last, until you get to the middle. And you can see that right in the middle, this is where we have Q2. So to find Q2, it would be in between these two numbers, meaning Q2 is found by saying 29 plus 31, and to get the middle of it, you say divided by 2. Okay, if we carry that over, it gives you 30 plus 30, which is 60, divided by 2 is 30. So Q2 is simply equal to 30, and now we can find the rest. So here's the thing. If this is the center, this is the middle, right? In between these two numbers. It's not those two numbers, it's the one in between. That's what we're taking. So we're going to look at this as this is the lower half, and then this is the upper half. Okay, so lower half and upper half. And so Q1 is the middle of your lower half. So you do the same thing. You could do the same thing to find Q1. So cancel 1 number, 2 numbers, 3 and 3, and then this is the exact middle. So the middle will be in between these two numbers. Okay, right in the middle of 21 and 21. So to find Q1, you say 21 plus 21 divided by 2, and then that gives you 21. So Q1 equals 21. And then to find Q3, you're also going to do the same thing. Q3 is the middle of the upper half of your data set. So cancel this one, 1 and 1, 2, 2, 3, 3, and then you can see these are in the middle. So that is simply 38 plus 42. Okay, if I take 2 out of that, that's 40, and then that's 40. So it's 40. Okay, Q3 equals 40. Q3 is equal to 40. So these are our numbers. Okay, the minimum value is 10. Q1 is 21. Q2, sorry about that, is 30. And then Q3 is 40. And the maximum is 48. And that is our 5-number summary. Moving on to the next question. Question 1.2 says, on the diagram sheet provided in answer sheet A, draw a box and whisker plot of the marks for grade 11B. Okay, so we have the 5-number summary. Let's just get that diagram sheet. Okay, so diagram sheet, and let's go ahead and put down the minimum and the maximum values. So the minimum value here is 10. So we'll just put a line down for 10. Just trying to make sure it's like at 10. So line down for 10 and then a line down for the maximum as well, which is 48. So that is 48, which would be in between, 45 and 50. So put that down. You can just always use a ruler, and measure. It can be a line down or a dot. I usually use a dot, to be honest. A dot and a dot. And then we're going to put down our quartiles. So our first quartile is marked at 21. So we'll go to 21 and then a line down here. And then second one is marked at 30. At 30, put a line down. And then Q3 is 40. So 40, put a line down. So at 21, I'm going to have to just write 21 here because, it's not really shown there. And of course, add 48 as well because that's not in our number line. Then just connect your quartiles and then finally connect this box with the quartiles to those dots. Okay, there's our whiskers. And that is our box and whisker diagram or our box plot. Okay, I also know that this was there, so maybe they would, ask us to compare things. So I'll just leave it like that. Okay, moving on to the next question. Question 1.3 says, calculate the mean mark of grade 11B. So whenever they ask you for the mean, just check if they ask for the standard deviation. So let's see that second question. Okay, so they do ask for the standard deviation. So with 1.3, we're going to find the mean, but we'll use the calculator. So for grade 11B, we have the info here, and let's put this into our calculator. So on your calculator, just go ahead and press mode, and then we're going to go for stat. Now we are inputting variables, just single variable data set. So go for 1 VAR, and then punch in all of these values into your calculator. Once you've punched it in, press AC, Shift and 1, and then go for the option that says VAR, okay, for variable, and we're just going to look for the mean. So the mean would look like this. This is the mean, and we'll go for that option, and you can see that our mean is simply 30, and that is our answer. Okay, now looking at the standard deviation, they say calculate the standard deviation of grade 11B. So to find the standard deviation, just press Shift and 1 to pull your info back again, and then go for VAR again. And then you're going to see the standard deviation will look like that. So the standard deviation, that is simply, let's just put that as a decimal, that is 11.46, and that is our answer. Moving on to the next question. Question 1.5 says, how many learners in grade 11B obtained a mark that is higher than one standard deviation above the mean? So to find out how many learners are in this category, we still need to find out what one standard deviation above the mean looks like. So you're looking at the mean and you're going a standard deviation above the mean. So we are adding a standard deviation, one standard deviation above whatever the mean value is. Okay, so that is mean plus standard deviation, and the mean is 30. So that is 30 plus the standard deviation is 11.46. So you can see how this is going to be 41.46. Okay, so we are looking for the learners. How many learners had a mark that was higher than this value? So 41.46, it's simple to find it once it's already in ascending order. 41.46, numbers higher than this would start at 42. So everybody here got higher than that value. So that's 1, 2, 3, 4 learners in grade 11B, and that would be our answer. Would finally conclude that there was a total of 4 learners. Okay, moving on to the next question. Question 1.6 says, taking the interquartile range of the two grades into account, comment on the performance of grade 11A and grade 11B. Okay, so taking the IQR, we need to use the IQR to comment on this. So let's get the IQR in each grade. So grade 11A and grade 11B. Let's find the IQR. The IQR, the interquartile range, is found by taking the range of your quartiles, really. So the highest quartile, the higher quartile minus the lower one, and we'll find this. Okay, so this is going to be equal to, in grade 11A, we knew that Q3 was 30, so that's 30 minus 11. Okay, 30 minus 10 is already 20, minus 1 is 19. So 30 minus 11 is 19. And let's see what grade 11B's IQR look like? So their IQR would be Q3 minus Q1. Here, that is 40 minus 21. Okay, 40 minus 20 is already 20, minus 1 is 19. Okay, so the IQR are exactly the same, but then we still have to comment on their performance with this. So we can tell them the IQR is exactly the same, but let's just see, based on that IQR, that range, let's just see how well they did compared if we're comparing that IQR. So here's what I mean. With the IQR, right, we're looking at Q3 minus Q1. So this data over here, right? So you can see that with this and how your info is really separated. The box and whisker diagram is just a way to present the info. What your info is actually telling you is this. For example, the whole class is there, right? We have from the minimum all the way to Q1, this would count as 25% of the class. So it means that 25% of the class scored a mark that was either equal to 21 out of 50 or less than 21 out of 50. And then 50% scored 30 or below 30. And then 75% scored 40 or below 40. And then finally, 100% scored either 48 or lower than 48. So your data has been cut into 4 quarters, okay? And each of them are 25%. So that's 25%, that's 25%, and that's 25%. So if we're focusing on the IQR, do you see that from Q1 to Q3, this is 25% of the learners that would lie here, and this is another set of 25% of the learners. This would be 50% of the learners. And so we can judge by just looking at the performance here versus the performance here in their IQR. Okay, just looking at the actual numbers. So here we knew that, I think, remember Q1 was like 11 and this one was 30. Okay, so this is Q1, this is Q3. You can see that here we have an entire 50% of the class scoring marks that are from 11 all the way to 30. But here in grade 11B, 50% of the class scored marks from 21 all the way to 40. So based on that, which class did better? It would be grade 11B. Do you see how their marks are more shifted to the right? Okay, so that 50%, okay, they did better than this 50% in grade 11A. Okay, so the IQR just being the same just means that they're equally spread out. Okay, so those Q1 all the way from Q1 to Q3, the marks they're equally consistent, really. I can't really say one is more consistent because the IQR is exactly the same. But we can see that this middle 50% of the learners, okay, they did better. Okay, the ones in grade 11B, they did better than the middle 50% of the learners in grade 11A. Okay, so with those quartiles. Okay, so we're just going to put this down and just phrase it. Okay, so grade 11B had a better performance. So though each IQR was 19, they were equally spread. Okay, they were equally consistent. Grade 11B's quartiles were higher than grade 11A. So that middle half of grade 11B still performed better than the middle half of grade 11A. And that is our answer there. Moving on to the next question. And the last question, 1.7 says, determine the percentage of learners in grade 11A who achieved less than 30 for the test. Okay, so less than 30 in grade 11A. Here's 30. So the percentage that received less than 30 would be this. And you just have to think about it with your box and whisker diagram. How much of a percent is this selected part? Well, we know that this, okay, Q1 is marked at 25%. So everything below this makes up 25% of your data set. This, okay, that's 50%. And then Q3, this would be 75%. And then finally, if you add that little 25%, that is 100%. So this is 75%. Okay, 25, 25, and then I think I explained it with this part as well, with this one, and 25. So that is 75% of your data set. So you can just tell them it is exactly 75%, and that is our answer. And that is it for question 1. Question 2 says, in the following diagram, D is negative 10 and 6, E, F, and G, which is 1 and 9, are vertices of a quadrilateral. The equation of EG, so this line, I'll just put that down, is 3x minus y plus 6 is equal to 0. You can see it's not in the standard form of the equation of a straight line. The diagonals of the quadrilateral bisect each other at a point K, as we can see. And then they tell us that the point F is on the x-axis and beta is the angle of inclination of EG. Okay, the first question is to determine the size of beta. So to find the angle of inclination of a line, you need the gradient of that line. Okay, because the gradient of the line is the change in y over the change in x. And these are the proportions for tan. Okay, so tan theta equals the opposite over the adjacent. If you have a triangle and you take a right angle triangle specifically, okay, and you have an angle, you see that if you take the opposite side, that is the change in y, okay, from that top y and then that bottom y, over the change in x, that's the adjacent side, that is tan. Okay, so tan theta, that's how we find this. So we say tan theta equals, and let's go ahead and find this. So tan theta equals the gradient. We need the gradient. To find the gradient of this line, it needs to be written in standard form. So it's currently 3x minus y, and that was a plus 6 equals 0. And all we have to do is make y the subject so that it's in its standard form. Y equals mx plus c. So you can see that y here is negative. Just transpose it, becomes positive. And now we have 3x plus 6. So we can see that the gradient of this line, EG, is simply 3. Okay, so y equals mx plus c. So it's 3. Therefore, to find this beta, we say tan beta equals this gradient of 3, and then transpose tan to get beta alone. So we're going to say on our calculator, the second function of tan, and then we say 3. So let's find this. So on the calculator, we say shift tan of 3, and there we go. It is 71.57 degrees rounded off to 2 decimal places, and that is our answer. Moving on to the next question. Question 2.2 says, calculate the coordinates of f given the equation of df is this. Okay, so the equation of df, and so you have to find the coordinates of f. F is on the x-axis, meaning this is an x-intercept. To find an x-intercept, you simply make y equal to 0, because at that coordinates, okay, on that coordinate, the y value is 0. So we have x plus 3y equals 8, and we're trying to find the x-intercept, so we make y equal to 0. And so that just becomes 0, and x is equal to 8. So it means that that point f is actually 8 and 0. So y value 0. You can also make sure you put that down because it's probably going to be helpful. Okay, moving on to the next question. Question 2.3 says, determine the coordinates of E. Okay, let's just see where E is. E is over here. And okay, so you see what we can do here. Do you remember how they said the diagonals of the quadrilateral bisect each other? So despite the fact that they didn't tell us what kind of quadrilateral this was, they didn't say it was a parallelogram, but they did say that their diagonals will bisect each other. So this is what it means for diagonals to bisect each other. If diagonals are bisecting, then it means that this line EG is cutting this line DF into 2 equal parts. So this is equal to this. Okay, so DK equals KF. And DF is also bisecting EG. So that cuts EG into 2 equal parts, meaning EK equals KG. So because of that, it means that the midpoint of this line EG is K, but that also means that the midpoint of line DF is also K. So they share the same midpoint. So the goal is find K, and that will help you find E. We can find K right now because we have D and F, those two endpoints. So let's use the midpoint formula to find K, and then we would find E. Okay, so using those 2 points, let me put those points down. Okay, so the midpoint of DF, we would find this by saying x1 plus x2, so this is just the midpoint formula, over 2, and then y1 plus y2 over 2. And so k, that midpoint, is simply found by saying we can take this as the first point, negative 10 plus 8 over 2, and 6 plus 0 over 2. Okay, if you say 8 minus 10, that gives you negative 2, divided by 2 is negative 1. And then 6 divided by 2 is 3. So this is k. So k is negative 1 and 3. But here's the thing. We know that the midpoint of DF is exactly the same as the midpoint of EG, because they told us the diagonals bisect each other. So therefore, to find that coordinates of E, those coordinates of E, we can say to find this, we're using the midpoint of EG. And to find this, we would say x1 plus x2, but let's just use these. So we don't know what this is right now, so you call it x and y. Okay, so we're using x and y and 1 and 9 as E and G. So this means x1 plus x2, that's going to be x plus 1 over 2, and then y1 and y2, so y plus 9 over 2. But we know now that the midpoints are the same. So it means that the midpoint here is also k, which is negative 1 and 3. And so because they're equal, we can equate these. We can make their x values equal and their y values equal. Because on one hand side, we have the actual midpoint. On the other hand, we have the calculation for the midpoint. So they represent the same thing. So this means that this x value of x plus 1 over 2 is actually equal to this x value of negative 1. And this y value of y plus 9 over 2 is actually equal to the y value of 3. And so now we can solve. So you can see that you can put this over 1, to create a fraction and then cross multiply. Or you could just see that 2 is in the denominator here. And we can multiply both hand sides by 2 to get it out of there. Now we have x plus 1 is equal to negative 2. And then transpose the 1. So x is equal to negative 3. And then here, same thing. Okay, here, if you cross multiply, you're just going to say 2 times 3 is 6. And y plus 9 times 1 stays y plus 9. Then transpose the 9. So y is equal to 6 minus 9 equals negative 3. And there we go. E is finally negative 3 and negative 3. And that is our answer. Moving on to the next question. Question 2.4 says, prove that DGFE is a rhombus. Okay, so to prove a rhombus, here's how we do this. You would have to first prove that a shape is a parallelogram before you can consider it as a rhombus. So with this shape, proving it's a parallelogram is actually, it's fine because they already told us that the diagonals of the quadrilateral bisect each other. Okay, one of the ways to prove that a shape is a parallelogram is if the diagonals bisect each other, meaning they have a common midpoint. Then it's already a parallelogram. So now to prove that it's a rhombus. Once you have proven it is a parallelogram, you can prove that it's a rhombus using one of the following options. So these two options. You can either prove that those diagonals, they actually bisect at 90 degrees. Then that makes this a rhombus. Or you can prove that a pair of adjacent sides, one pair of adjacent sides are equal. Okay, so you can choose which one you want to use. Now, I would rather go with the proving that the diagonals bisect at 90 degrees because to do that, to show that diagonals bisect at 90 degrees, or in other words, diagonals are perpendicular, you can just use the property of perpendicular lines, which is that if you take the gradient of the first line multiplied by the gradient of the second line, if these lines are perpendicular, the product of the gradients is negative 1. And I know we found the gradient of one of these lines already, okay, one of the diagonals, which was this, EG. So, see, that's already done. All we have to do is find the gradient of this line. Okay, so I would still confirm first that it is I will still conclude that it is a parallelogram first, okay, because of the diagonals bisecting each other. Okay, so it's a parallelogram because the diagonals bisect each other, and then further prove that it's a rhombus. So we already have the gradient of EG. Okay, we found that initially in the first question. The gradient of EG is 3. Okay, and all we have to do is find the gradient of the other diagonal. The other diagonal is DF. So use D and F, and let's put those points down. The gradient is found by saying the change in y, so y2 minus y1 over x2 minus x1. So this is equal to, and we're going to say 6 minus 0 over negative 10 minus 8. So this is positive 6. This becomes negative 18. And you know that 18, okay, 6 goes into 18 three times. So this is negative 1 over 3. See how this makes a lot of sense. So the gradient of df is negative 1 over 3. So now this is all we have to do. We can show them that if you take the gradient of EG and you multiply it by the gradient of df, look at what they give us. 3 times negative 1 over 3 equals negative 1. Okay, so because the diagonals are perpendicular, what it means is they bisect at 90 degrees. So I'm just saying that df is therefore perpendicular to EG. And finally, we can conclude that DGFE is a rhombus because the diagonals specifically bisect at 90 degrees. And that is our answer. Okay, so to prove a shape is a rhombus, you prove it's a parallelogram first, and then one of those two properties. And that is our answer, and that is it for question 2. Question 3 says, in the diagram below, A is the point where we have negative 2 and negative 1, and then we have B, which is negative 3 and 4, and C, which is 1 and 5, and then also give us D. So D is 5 and Y, okay? And the first question is to find the length of AC in simplified third form. Okay, so AC. So when we have the coordinates, we can just use the distance formula. Distance equals the square root of x2 minus x1 all squared plus y2 minus y1 all squared. So AC equals, and we can take this as the second point, so point number 2, and this is point number 1. So x2 is 1, that's 1 minus x1, which is negative 2, and then all squared, plus y2 minus y1, that's 5, minus negative 1, all squared. And just go ahead and punch that into your calculator, and let's get our answer. And our final answer is 3 square root 5 units. Okay, and that is it for this question. Moving on to the next question. Question 3.2 says determine the gradient of BC. So use the gradient formula. Okay, so this is y2 minus y1 over x2 minus x1. Okay, so the gradient of BC using B and C, we have these 2 points. Okay, so that is y2 minus y1, 5 minus 4, 5 minus 4, all over, and we have 1 minus negative 3. So 1 minus negative 3, you can see 5 minus 4 is 1, and that's just going to be 4. So our answer is 1 over 4. That's the gradient of BC. Moving on to the next question. Then question 3.3 says, determine the value of y if B, C, and D are collinear. So they're collinear, meaning they lie on the same line. So if they lie on the same line, then this means that the gradients would be exactly the same because this is one line. So the slope is exactly the same all through. So how we can find y, it's just one missing value. We can find it using, see, we can say, look, we know the gradient of BC. Okay, so we can go ahead and try to find the gradient of, let's say, CD or even BD. Okay, so in other words, we're just saying the gradient of BC is exactly the same as the gradient of, I'm just going to go with CD, okay, because they lie on the same line. Okay, and then I'll just put the points down. Okay, so the gradient of BC, we already found that, okay, to be 1 over 4. If we rewrite this as 1 over 4, this is equal to, and it's equal to the gradient of CD, so this is C and D. Well, I'm just going to go with this being y2. So y minus 5 over 5 minus 1. So this is 1 over 4 is equal to, and this is just y minus 5, and then that just becomes 4. Okay, the denominators are exactly the same, so you can just equate the numerators. This is because you can get rid of the 4 simply by multiplying both hand sides of this equation by 4, and so you see 4 cancels in the denominator. So all we're saying is y minus 5 is equal to 1, and so therefore y is equal to 1 plus 5, which is 6. And that is our answer. The value of y is simply 6. Moving on to the next question. Question 3.4 says, if H is a new point such that AH is perpendicular to BC, determine the equation of AH. Okay, so with these questions, you actually don't need to sketch anything. You just have to take notes of everything they're saying. So H is a new point, no problem. AH is perpendicular to BC. That's where you need to start taking notes. So AH is perpendicular to BC, which means that if you take the gradient of AH and you multiply it by the gradient of BC, they will give you -1 because they are perpendicular lines. And so with this info, we need to determine the equation of AH. Well, the thing about AH is we don't know what H is, but we do know what A is. So it means that it goes from A to H. But we know that A, using our diagram, okay, is -2 and -1. So that is -2 and -1. And we're just going to do this. So what is the gradient of BC? Did we at any point find this? Yes, we did. It's 1/4. So to find this, we say the gradient of AH multiplied by 1/4 is equal to -1. And so to finally find this, you can divide both hand sides by 1/4 since it was multiplying to AH, or you can multiply both hand sides by 4. And then that way it will get rid of that 4 as a denominator. So we just have M of AH, okay, the gradient of AH equals, we multiply by 4 here, -4. Okay, we have the gradient and we have 1 point on the line. So we can find its equation. We can use y equals mx plus c, and I'll just go ahead and use that here. Y equals mx plus c. We can see our gradient is -4, so x plus c. And then to find c, just substitute 1 point on the line, which is -2 and -1, okay, in place of x and y. So in place of y, we say -1 equals, and we have -4. And then in place of x, -2 plus c, and solve for c. Okay, remember that this is the equation we'll put it back into because we're just trying to find c. So -1, that becomes +8, but when you take it over, it becomes -8. So -1 minus 8 is -9. So c is simply equal to -9. And finally, y is equal to -4x minus 9. And that is our answer. And that is it for question 3.4. And that is it for question 3. Question 4, 4.1 says, in the diagram below, P, which is x and -24, is a point such that OP is equal to 25 units and R is 12 and 0. Okay, with ROP being equal to beta, where beta is greater than 180 degrees but less than 270 degrees. Calculate the value of x. Okay, so you can see that we have a trig diagram here, and they've given us the radius and also they've given us the value of y. Okay, so the value of y, if you were looking for this point, it would be x units to the left and 24 units down. So that is the value of y. We'll go ahead and draw a line up to the x-axis, and it's perpendicular to the x-axis. And so this is -24, okay? So that is the y value it represents. And all we have to do is find the value of x. So we can use Pythagoras here. Okay, so to find that x is the shorter side, so we'll say x squared is equal to, and we'll take the longer side squared, which is 25 squared, minus -24 all squared. So x squared equals, and we can just find this, and this is 49, and then finally find x. So we'll square root both hand sides, but remember to consider the positive and negative solution. So x is finally equal to, based on the diagram, you can see that x is in the negative part of the x-axis. So we have -7, okay, if you square root 49. So this is -7, and that is our answer. Moving on to the next question. Question 4.1.2 says, determine the value of each of the following without the use of a calculator. So A, we need to find the value of sine beta. Okay, so in reference to this angle, and we already have the diagram. So sine from SOHCAHTOA is opposite over hypotenuse. So looking at this triangle, we'll take the opposite side over the hypotenuse. Okay, so that is -24 over 25, and that is the value of sine beta, -24 over 25. Moving on to the next question. The next question, we have to find the value of cos 180 degrees minus beta. Okay, so we can reduce this first. Using your cos diagram, you know that 180 degrees minus beta or minus theta. This is the reduction where sine is positive. So because we're using the function cos here, we know that cos is negative in this quadrant, meaning it becomes negative cos beta. And now we need to find the value of cos beta. So cos beta, we would find that, remember, cos is adjacent over hypotenuse. So the adjacent side, the side next to that angle, is negative 7 over the hypotenuse is 25. So we just have negative and then negative 7 over 25. Then once we multiply in, this becomes 7 over 25. And that is our answer. Moving on to the next question. The next question is we need to find the size of tan squared negative beta. So do you see that the beta is negative? So when your angle is negative, simply add 360 degrees to this. So it becomes tan squared, and this is 360 degrees, okay, positive 360 degrees minus beta. And you know that tan 360 degrees minus beta, based on where 360 degrees minus our reference angle is, this is in the quadrant where cos is positive, but tan is negative in this quadrant. So what happens is you have this, but then tan is negative. So you end up with negative tan beta, but still remember that this is squared. So it gets squared and ends up becoming positive. So now this is positive tan squared beta. And so tan squared beta, we would find this using SOHCAHTOA, opposite over adjacent. Okay, so that opposite over adjacent is negative 24 over negative 7. And so that is negative 24 over negative 7. And then it gets squared. So this is finally equal to, we can just square that. So you know that it's going to become positive because we are squaring it. But regardless, they were going to be positive because they're dividing, okay? Negative divided by negative is a positive. So our final answer is 576 over 49. And that is our answer. Moving on to the next question. Question 4.1.3 says, T is a point on OP such that OT is equal to 15. Okay, so this refers to this diagram, and I'm just going to bring it down. Okay, so we know that it's a point on OP, so T is a point, we just put that down, okay, T, such that OT is equal to 15. So this is equal to 15 from O to T. And the question is to show that T is negative 21 over 5, and okay, so the coordinates of T are this without the use of a calculator. So here's the thing. Yes, they give you a new point, but the thing is this point still lies on OP. So you see, because this is the radius of this new diagram we're going to draw, here's the thing about it. Beta would still be the exact same size. So that means if you were trying to find the size of sine beta in this triangle, this new triangle, where we'll find this triangle by drawing a line up to the x-axis, okay, perpendicular to the x-axis, of course, and so that will be a dotted line that we have, and it's perpendicular. Sine beta, cos beta, tan beta, they would still be exactly the same here because they refer to the same angle, okay, the same size with your angle. So it's all based on the size of the angle. So sine beta, cos beta, tan beta, they would be a certain thing based on the size of that angle. Since it lies on the same line, they have the same size. So we know that we can actually find this coordinate, okay, the x coordinate and the y coordinate, using the information we have in this bigger triangle. Here's how we can do this. You see how the x value, right? To find an x coordinate, we use the adjacent side. And we already have the hypotenuse. So to find the value of x, because we can see that x, okay, refers to the adjacent side, x, and we already have the hypotenuse, we can go ahead and use that here. So we're going to use adjacent and the hypotenuse side, meaning we're going to use the function cos, okay, because from SOHCAHTOA, you know that adjacent and hypotenuse, they would go cos. So here is the thing about this. You see cos beta in our previous question, right? I think at some point we found it. Okay, we found negative cos beta. But we know now that cos beta itself is equal to negative 7 over 25. So yes, we know that cos beta is equal to negative 7 over 25. But we also know that cos beta would also be equal to negative 7 over 25. Okay, since they're drawn using the same angle. So currently this point really doesn't have any coordinates. We'll just call it x and y. Okay. So to find this, we're going to go ahead and say we know that in the red triangle, cos beta is currently, now the x value is your adjacent side, okay? Because that's the one next to the angle. So the adjacent side over, and the only thing we have is the hypotenuse. So we'll take it over the hypotenuse of 15 in that red triangle. But because cos beta and cos beta are equal, we can equate these, okay? Because they're drawn using the same angle. So their trig ratios will all be the same. So finally, we can just tell them that negative 7 over 25 is actually equal to x over 15. And now we can solve for x. You see that to get x alone, you need to just multiply both hand sides of this equation by 15 to get rid of that 15 in the denominator. Finally, x is equal to, and let's find this, 15 times negative 7 over 25. And that x value is indeed negative 21 over 5. Okay, now you see in the same way we found the x value, we will find the y value. With the y value, you see that if you need to find the y value and the only thing that you had was the hypotenuse, it means that you have the y value is the opposite side. Okay, so we're looking at the opposite side and the hypotenuse, meaning O and H means you're going to use the function sine from SOHCAHTOA. Okay, so we're going to use sine. So to find this, we'll say sine of beta, and sine of beta, let's find sine beta in the bigger triangle first. We know that it's going to be exactly the same. Sine beta in the bigger triangle was negative 24 over 25. So we'll say this is negative 24 over 25. And sine beta in the red triangle, and let me just leave that in red, sine beta is equal to, that is going to be y over 15, okay? Opposite over hypotenuse. So this is y over 15. And we know that they're exactly the same since they were drawn using the same angle. So it doesn't matter where this point is, okay? As long as it is a point that is on this line, even if it was extended and then it was there, as long as they are collinear, they would still form the exact same angle size when you measure from the x-axis, meaning all their trig ratios will be the same. So this is finally equal to, and we're going to equate these. So this is negative 24 over 25 is equal to y over 15. And how do we solve for y? We solve for y by multiplying both hand sides of the equation by 15. And so finally, y is equal to, and let's get our answer there, and that is indeed negative 72 over 5, like they said it would be. So there, we can finally conclude that t is equal to, so the x value, t is, as we can see, negative 21 over 5 and negative 72 over 5. And that is our answer. And that is it for this question. Moving on to the next question. And then B says, determine the area of triangle ROT. Okay, so the area of triangle ROT. So that is using this new point T that we have. How do we find this area? Remember that we just found T, and I'm just going to put that down here. Okay, so ROT, this triangle, is what they're referring to. So this triangle over here, we need to find the area of this triangle. Okay, so it is an obtuse triangle, but the first thing you should always do with triangles in general is to find their area, try to use half base times height before using anything else, before trying to use the area rule. So to find this area, we're just going to go ahead and say a half multiplied by the base multiplied by the perpendicular height. So the base, we can clearly see that we can just use this as the base. Okay, RO can be the base. And then what is the perpendicular height? The perpendicular height will always be drawn from the highest point of the triangle, so that will be T in this case, and then down, okay, perpendicular to the base, or at least an extension of that base. You can see that this is the height over here. So this is the height, meaning, as you can see from the previous question, this is the y value, okay? This is the x value over here. This is the y value, so that's the y value, meaning that is the height. But of course, you're not going to take it as a negative value. It's a height, so it needs to be positive. So the height is 72 over 5. And we know the base is as well. The base is RO. It goes from the center and then 12 units to the right, as you can see. So the base would be 12 units. Okay, so we've got a triangle with a base of 12 units and a perpendicular height of 72 over 5. And that's how we would find that. So just say finally, the area of triangle ROT would be found by saying a half multiplied by that base of 12 multiplied by the perpendicular height of 72 over 5. And that would give us our answer. And then as a decimal, this is just 86.4. Okay, and it is not in centimeters, it's just in units. So we can say square units, so units squared. And that is our answer. Okay, moving on to the next question. Question 4.2, the last question for question 4, says simplify to a single trigonometric ratio. And we've been given this. So you see with this, you're going to use cofunctions, you're going to use reductions and certain rules that you need to know. So let me put down cofunctions and also our reduction diagram. Okay, so here is our reduction diagram. And just remember that with your cofunctions, sine 90 degrees minus theta equals cos theta. So it just changes. And then cos 90 degrees minus theta equals sine theta. Sine 90 degrees plus theta equals cos theta. And finally, cos 90 degrees plus theta equals negative sine theta. That's the only one that changes to a negative. Okay, so just remember those. Okay, so here we go. We have tan 225 degrees. We can actually just simplify this by saying this is tan, and we're just going to see which quadrant does this lie in. 225 degrees is an angle that is greater than 180 degrees, but less than 270 degrees. So we will use this reduction, meaning it's 180 degrees plus what gives you 225. That is 45 degrees. Then we have plus, and this is sine, and we can reduce that. Okay, so 180 degrees minus theta, that is in sine's quadrant. And we can see that sine is positive here. So this remains positive, sine theta. And then cos 90 degrees plus theta, remember that is the only one that changes to negative. Okay, so that becomes multiplied by negative sine theta. And then all over cos 90 degrees minus theta, which is equal to sine theta, and then multiplied by, and then here, you see what is going on here. Yes, they put the angle over here, which from the order you can see here, it should be put after the angle with the numerical value. But overall, what's going on here is that this angle is negative. Okay, so if you have negative theta and then minus 540 degrees, your angle is ultimately negative. And so what you have to do when the angle is negative is simply add 360 degrees until the angle is positive. Okay, if you take 500 and negative 540 degrees, you add 360 degrees, still negative, then add 360 degrees again. And now it's finally positive, and it's positive 180 degrees, meaning that is simply equal to sine, and we'll just say sine, and we have a positive 180 degrees, which we write first, and then this theta, which is negative theta. And then we have this is equal to, and now we can reduce this. Okay, so tan 180 degrees plus 45 degrees, you can see this as theta. So that means this is in tan's quadrant, where tan actually is positive. So this becomes positive tan 45 degrees. And then these multiply to become negative sine squared theta all over. And here we have sine theta multiplied by, see, 180 degrees minus theta, this is in sine's quadrant, so this just stays positive sine theta. And here, tan 45 degrees, you can use your calculator. It's going to just be equal to 1. And then we have minus sine squared theta all over, and then sine theta times sine theta is sine squared theta. So it needs to be simplified to a single trigonometric ratio, meaning there's something we can actually do up here. Remember the identity that tells you that sine squared theta plus cos squared theta is equal to 1. Well, with this identity, you can actually create one that will have cos squared theta as the subject. So if you leave cos squared theta here and you take sine squared theta over, then you still have 1 and then minus sine squared theta. So that means in place of 1 minus sine squared theta, we can just replace this with cos squared theta. And so what we have here is cos squared theta over sine squared theta. And this can be simplified further. Remember how tan theta is equal to sine theta over cos theta. So what happens when you swap the numerator and denominator? What will this be equal to? So it's not sine theta over cos theta, right? It's cos theta over sine theta, of course, with a squared. So what this would be equal to is 1 over tan theta, because the numerator and denominator have switched places. So 1 over tan theta, if we had 1 over tan theta, it would be equal to 1 over, sine theta over cos theta. And then if you went ahead to actually divide this, you'd be saying 1 divided by sine theta over cos theta. And this division using tip and times would change into a multiplication. So we say multiply by cos theta over sine theta. So we tip this, we swap the numerator and denominator, and we change the division to a multiplication sign. And so do you see how it's cos theta over sine theta? So that is why at the end of the day, this would simply be equal to, so cos squared theta over sine squared theta, it's actually equal to 1 over tan squared theta. And that is our answer. And that is it for this question. And that is it for question 4. Question 5 says, in the diagram below, f of x, which is a cos a half x minus 1 over 2. So that is the cos graph that we have. And then g of x is negative. Okay, so let's just mark these. A of x, the cos graph, as you can see, that is this graph. Okay, so I'll mark that. And then g of x negative 2 sine x plus p, that is the sine graph. And that is this graph over here. Okay, and they say they are drawn for where x is greater than or equal to negative 240 degrees, but less than or equal to 240 degrees. So it goes from that to that. And question 5.1 says, write down the amplitude of g. So the amplitude. You see, the amplitude of a graph, we can find the amplitude of a sine and a cos graph because of their curves. So the amplitude of a graph is the height of that graph from its midline. Okay, so from the middle. So if you see a sine graph, okay, and it just says y equals sine x, it depends on what is in front of that sine x. Okay, we can see here there's an invisible 1. So it means that the highest it reaches is 1 and the lowest it reaches is negative 1. You would also have to consider whether they were shifts. So if this graph was shifted up or down, so if it was plus 5, then, it would be, the amplitude would still be 1, but then finding it may be a little different because the maximum here would not be 1 and the minimum would not be negative 1. Okay, so that's just an explanation on that. So to find the amplitude of g, that is the sine graph, you can see that there is a negative 2 in front of sine and then all of that. Okay, so this graph has not been shifted up or down. This is x plus p. Okay, you're adding to the x. If you're adding to x, this is not an up or down movement. This is a left or right movement because you're only affecting the x value. Okay, if you take a point and let's say you add to the x value, let's say we add 2 here. This becomes the point A, which is now 3 and 2. Okay, it moves from this point to the right. Okay, so that is a right or left movement, meaning we're going to look at the absolute value of this. If this is negative 2, remember the amplitude is a height. Okay, so it's the height from the midline. So it cannot be negative, meaning it's positive 2. Okay, so take the absolute value of the coefficient of that sine. So the amplitude is simply equal to 2. And that is our answer. Moving on to the next question. The next question, determine the period of f. So the period of a graph, we can see that f is the cos graph, and how we can determine its period is always focus on the value in front of x. Okay, x is your degrees, the angles that we have. Whatever is placed in front of x will affect those angles, and so it will also affect how quickly or slow your graph completes a cycle. So it's a cos graph. Naturally, a cos graph completes a cycle in 360 degrees. Okay, it takes 360 degrees to complete a cycle. But if you tamper with that value in front of that x, it's going to change it. And how we work with this is like this. You're going to have to think about the original period of that particular graph. It's a cos graph. Its original period is 360 degrees. And you're going to take that and divided by whatever value was in front of x. In this case, it was a half. So we'll just say divided by a half. 360 divided by a half is 720 degrees. So that means this cos graph is completing a cycle not in 360 degrees like it would have done before. It's completing a cycle in double of this. So it's taking longer to complete one cycle, meaning it is going to be a wider graph. That's why it looks like that. Okay, so there we go. Of course, the other parts of it have been cropped out, because it does not fit into this interval. And that is our answer. Moving on to the next question. Question 5.3 says, determine the values of A and P. Okay, so the values of A and P, that's in our graphs. Let's look at the graphs and just see what's going on. Let's start with the cos graph. So to determine the value of A, remember how that value also helps with the amplitude, okay, the height of the graph from the midline. We see that we're working with the sine and cos graph, so we can actually find the amplitude. But with this graph, do you notice that it also has minus a half? Notice where that minus a half is. It's not saying minus a half to the x, okay, like this P is doing. Okay, I don't know if this is plus or minus, we'll still see. But it is outside, meaning this is a downward shift. If it's not being applied directly to the x, it's an up or down shift. But we can see it's minus, so this graph was shifted a half units down. So let's think about where it used to be. If it was shifted a half units down, it means it used to be here. We would move it a half units up. So this is negative 1.5. Let's move it back a half units up, meaning that's what it would have looked like, okay? So that period would have been changed, but then it was going to reach a lowest of negative a half. So what we can see from this is the height of this graph, okay, from the midline would be the x-axis in this case. If we had to shift it back a half units up, okay, then the midline, the middle, okay, would be on the x-axis. So it means that the height of this graph is 1 unit. So since we know that the height is 1, we still have to figure out whether this is positive or negative, okay? So how we figure that out is based on the way the cos graph normally looks. Let's think about that. So from 0 to 360 degrees, the cos graph looks like that, right? Now looking at this, I'll focus on 0 degrees because it has not been shifted to the left or the right. So all of these angles should still be consistent. It was only shifted down. And of course, that half was added in front of x. So naturally, okay, on the original cos graph, y equals cos x, we know that at 0 degrees, we have a y value of 1. Let's see what's going on here. At 0 degrees, after shifting that graph a half units up, we have a y value of negative 1. So what does that mean about this graph? And you can also test it out with the other points that you're seeing. But I'm not really seeing other clearer points. The best point I can see is 0 degrees and this negative 1. So because it has not been shifted to the left or the right and just been shifted down, but we can see that on the original graph, we have 0 degrees and 1 as our first point. But here it's 0 degrees and negative 1. It means that that value of 1, because we saw the amplitude was 1, right? The height of that graph was 1. That was multiplied by negative 1. That is the reason why it's saying 0 degrees and negative 1. Okay, so the value of A is actually a negative 1. So A is equal to negative 1. You do this by observation, understanding what the original graph looks like and comparing it to this one. Okay, so we know the value of A. We can just, push this back here and let's deal with the graph of G. So with the graph of G, it's a sine graph. And this sine graph has been shifted either to the left or the right. As you can see, a P has been added to X, okay, directly to X. Also, the amplitude has been changed, okay, the coefficient of sine has been changed. It's negative 2. So we should also keep that in mind. Think about what the original sine graph looks like, that y equals sine x, the mother graph. The shape looks like this. It just goes up and then down and then like that. The highest it reaches is 1, the lowest is negative 1. But right now they've changed this to a negative 2. So what would happen here is if you just changed it to 2, like 2 sine x, what would happen is this would just reach a highest of 2 and a lowest of negative 2. Now, if you change it to negative 2 sine x, this now changes. So all the y values get multiplied by that negative. And it ends up looking like this. Okay, because you're looking at the y values, you're saying 0 degrees and 0. If you multiply 0 by -1, you still get 0. This would have been 90 degrees and 2. If you multiply that by -1, you get -2. This is the reason why now this point appears here. And then you have this, and then this, which should have been -2, is now 2. So this is what the graph ends up looking like. So even with this graph, we are able to now compare it to this blue graph here to understand how it was shifted. And this is how we do this. So you can focus on finding this exact shape. So where it goes like this and then up and then like that. And I can see that already over here. Okay. It's not the complete shape of it, but I can see that over there. This endpoint, which was supposed to end at 360 degrees, look at where it ends here. It ends at 60 degrees. So what this means is this graph could have been, okay, so it could have been shifted either to the left so that it ends up looking like that. But you see, the problem with this is not really a problem, but it's something that you would already catch that there's something wrong with that. If you had to take it from this point, right? And you can see that 60 degrees and the y value of 0 are here. If you had to shift it to the left, right? You'd have to shift it from this 360 degrees all the way to 60 degrees. That would be how many degrees to the left? That would be a whole 300 degrees to the left. Never take the big value like that, okay? That big shift, don't take that. I'll copy that graph and then I'll just paste it here just so that you can see what happened. You see the sine graph will repeat itself every 360 degrees. So 360 degrees later, you'd have another cycle that looks like this. And 360 degrees before this, you'd have another cycle over there. And so what happened is this graph, okay, on this part, it was actually shifted 60 degrees to the right like that. So it's the repetition of that cycle. Okay, so this went 60 degrees to the right. So it would have been here at 0 degrees, but if it shifts 60 degrees to the right, then it ends up looking like that. And then do you see how it ends up looking like this pink part, okay, that goes up like that and then like that. Okay, so we know the original graph was supposed to look like this, okay, that repetition. And then it was shifted 60 degrees to the right. Okay, so now that you know it was shifted 60 degrees to the right, we need to interpret this, okay, or tell them at least the value of P. You first interpret it with words. You know that it was 60 degrees to the right. Now here's how we apply a right movement. If you are applying it to the equation of a function, if it was shifted to the left, you're going to add, okay? Left means add to this, okay, in the equation. And if it was shifted to the right, you're going to subtract. So this means that the value of P for that to shift 60 degrees to the right is actually negative 60 degrees. And that would be our answer. So A is equal to -1 and P is equal to negative 60 degrees. And that is our answer. Moving on to the next question. Question 5.4 says, for which value or values of x is f multiplied by f of x less than or equal to 0? Okay, so when you multiply them, they give you a value less than or equal to 0. Okay, so the only way this is possible is if the function of f had, remember, they're saying f of x and g of x, so it refers to their y values. If the y values of f were positive and you multiply them by the y values of g, which were negative, then they would give you a negative, okay, a value less than 0. If the y values of f were negative and the y values of g were positive, they would also give you a negative. And if either one of them were equal to 0, they would give you equal to 0. So this is what we are looking for. Let me pin this and let's see if we can find this in the diagram. Okay, so this is what we have. And now let's see. You see, when f of x is positive, where we're looking for where f of x is positive, in other words, where f of x, the y values of f are greater than 0, okay, that's where they are positive. This would be all the places where we have positive y values. We know that positive y values lie above the x-axis over here. This is where we have positive y values. So you would have to take the parts of f that have positive y values, which are specifically above the x-axis. And then where your y values are negative, okay, for example, where g of x is less than 0, okay, where it's negative, this would lie below the x-axis because this is where we have negative y values, okay? So all we are doing is we're looking for points on this graph or places where the y values of f, or where f is specifically above the x-axis, and then at the same time g is below the x-axis. So where do we see that? F is above the x-axis all through here. But for these same values, okay, you can use a vertical line to better understand this. Use a ruler really. So for these same values, the graph of g needs to be below the x-axis. See, at that point over there, at this x value of negative 120 degrees, at negative 120 degrees, that is where the graph of g is specifically equal to 0. Okay, so, and then after this, you can see there it's above the x-axis. This one is below the x-axis. Above the x-axis, that's below. So it's working all through here, okay, until this point. Because if you go after this, you see now that the blue graph is below the x-axis, and so is the red graph. That's not what we want. We want one to be above and the other to be below. Okay, same thing over here. If you see that on this side, the blue graph is below the x-axis, meaning f has a negative y value here. But for the same x value, g unfortunately also has a negative y value. They need to have opposite signs. So it works all through here, starting at negative 120 degrees. If you line this down, you can see that it's values that are greater than or equal to negative 120 degrees, but less than or equal to 60 degrees. So we can put that down. Okay, so x is greater than or equal to negative 120 degrees, but less than or equal to 60 degrees, okay, positive 60 degrees. And now let's see if we have this anywhere else. Remember, it's equal to these because at these specific points, these are x-intercepts. This is where the y value is equal to 0. When you multiply them, they should give you a value either less than 0 or equal to 0. Okay, so for negative 120 degrees, that actually does work because that y value of 0 times this negative y value, they give you 0. Okay, so that's what we have there. And then let's go ahead and look for where the graph of f has a negative y value, and at the same time, the graph of g has a positive y value. So we're looking for where the graph of f has negative y values, meaning below the x-axis. The blue graph, the graph of f is below the x-axis here, okay, just all through here and all through here. But for the same x values, the graph of g needs to be above the x-axis. So again, use a vertical line or ruler and then just check. See, does that work over here? Not really. We'll talk about negative 240 degrees because that's actually fine. That actually works. You see, at negative 240 degrees, the graph of g has a y value of 0. Okay, that's an x-intercept there. So if you take that y value, 0, multiply by whatever y value is here for the same x value, okay, you get 0, which is one of the requirements. So we need to make sure we take that as well. And if we keep moving to the right, you see how, unfortunately, they both lie below the x-axis. So it doesn't work all through here. They're just below the x-axis. What about on this side? Okay, at 60 degrees, that's definitely one. We already have that point down. But if you keep moving to the right, unfortunately, you see how both graphs lie below the x-axis? So they don't work. Okay, they don't work all through there. And then they work at 240 degrees because at 240 degrees, we have an x-intercept. Okay, you see that the graph of f has a y value of 0 and the graph of g also has a y value of 0. So 0, okay, that y value times that 0, it still gives you 0, which is one of the requirements, less than or equal to 0. Okay, so the solutions we have there is simply, we don't have any of the solutions like directly on the graph, but just these points, negative 240 degrees and positive 240 degrees. So we can just say, this is our answer. I'll put it in order. So let's put that there first and say x is equal to negative 240 degrees, or x is greater than or equal to negative 120 degrees, okay, less than or equal to 60 degrees, or x is equal to positive 240 degrees, and that would be our answer. Okay, so that's our answer to this question. Moving on to the next question. Question 5.5 says, if h of x is equal to 2 cos x plus k, and h of x is also equal to g of x, write down a possible value of k. Okay, so this is a question that has shown up a lot. And this is how you can look at it. So we know that h of x is equal to 2 cos x plus k. I see that it's there, but I'm probably going to need to move it. But we also know that h of x is also equal to, so h of x is also equal to g of x. Let's just remember what g of x is. G of x is, okay, negative 2 sine, and then x minus 60 degrees because we know the value of p. So this is equal to, I will just put it down here, it's fine. Negative 2 sine x minus 60 degrees. So they're asking you, what should k be for this equation to be equal to this equation, since they both stand for h of x? Okay, do you see a very obvious problem with this? If these two equations should be equal, we have a problem. One says cos, the other says sine. So we need to change this, okay? So of course we can't really work with this one because we're trying to get this one to look something like that, okay? So we can figure out what exactly k is. So we need to change this sine to cos. And how do we do that? We do that using cofunctions. So this says sine, okay, I'm just going to rewrite it like this. Look at how we can write this. I'm going to rewrite this as 2 multiplied by negative sine x minus 60 degrees. And then I'm going to try to change that. Okay, that negative sine x minus 60 degrees. With cofunctions, the only cofunction, do you remember a cofunction where sine becomes negative? Okay, so we could see this as negative sine A. Do you remember that cos 90 degrees plus theta, that this is equal to negative sine theta? Let's just call it A, to simplify this. So cos 90 degrees plus A equals negative sine A. So that means in place of negative sine A, we could just replace this with cos 90 degrees plus A. So if this became cos 90 degrees plus A, then you can see that the A we are referring to here is actually this angle. Okay, x minus 60 degrees. Okay, you see, negative sine x minus 60 degrees, negative sine A. So in place of A, we'll just substitute x minus 60 degrees. So I'm changing this to 2 multiplied by, and this is cos 90 degrees, and in place of A, I'm just saying x minus 60 degrees. Okay, it's just adding, so you can just say plus x minus 60 degrees. No sign changes because you're just adding. So that's what we have there. And then simplify this. You can see you have numbers here. This is 2 cos 90 degrees minus 60 degrees gives you 30 degrees. And I'm also just going to check the order in which this has been written. They wrote the x first and then plus k. K just stands for a number. So let's rewrite it with the x first. And we know 90 degrees minus 60 degrees equals positive 30 degrees. So for which values of k, okay, or what should k be for this h of x to be equal to this h of x? Can you see that? K simply needs to be equal to 30 degrees. Okay, so there we go. That's h of x. And so they said they want us to solve for k. So finally, we can see that k must simply be equal to 30 degrees for that to be exactly the same. And that is our answer. And that is it for question 5. Question 6 says, a candle holder is made in the shape of a hemisphere where a conical section is drilled out for the candle wax. Okay, so that's the part that is drilled out. In the diagram below, the radius of the hemisphere is represented by r, which is this, where st, okay, so st is equal to vt, okay, and which is equal to r. Okay, so that is from the radius to the surface, okay, the surface of that hemisphere. The radius of the cone is represented by r, small letter r, okay, where tw is equal to r. The angle at the vertex of the cone is given by theta, okay, so that is the angle. So if you kind of like cut this into a flat shape, you can see this is the angle they are referring to. Okay, and then they also give us some formulas. They tell us that the volume of a sphere is 4 over 3 pi r cubed, okay, big letter r in this case because we're using that. But remember that we are working with a hemisphere. And they also give us the volume of a cone, okay. So the first question, 6.1 says, express r in terms of r and, so big letter r and theta. So when they're asking you to express something in terms of other things, they're saying find an equation for r and your answer should include r and theta. So let's look at how we can do that. They want us to express r, which is this, in terms of big letter r and theta. The only way we can do that, because remember how TV is equal to ST, which is equal to R. So this is also R, meaning we can use this shape over here. We have a 90-degree angle over here, and we can use this triangle that we see here, and we can express R in terms of it. Okay, so do you see that in this triangle, we have this entire angle, theta, but we're going to have to use half of it because we are cutting it from the center. Okay, it's going from the center to that circumference. So it means that this line bisects this angle, meaning if this is theta, this is half theta, or we can just see this as theta divided by 2. Okay, that is this angle over here. So if we have this angle and we have to find this side using this, we can just use our trig ratios here. So see that R is right opposite this angle that we're using here, this half of it, right? And so this is the opposite side. And then this R is next to that angle. This is the adjacent side. So since we're using opposite and adjacent, it means we need to use tan. So we can go ahead and say, okay, remember from SOHCAHTOA, tan is opposite over adjacent. So we can go ahead and just say that tan, and the angle we're using is theta over 2. So tan theta over 2 is equal to the opposite over the adjacent, which is small letter r, over big letter R. And then all we have to do is express R, okay, in terms of R and theta. So let's go ahead and get rid of this R, and we can do that by multiplying both hand sides of this equation by R. And now that R is gone in the denominator, finally, this R is equal to, multiply there, we get R tan theta over 2, and that is our answer. Moving on to the next question. Question 6.2 says, show that the remaining volume of the hemisphere can be represented by this. So that the volume, that remaining volume, is going to be pi r to the power of 3 over 3 and then multiply by 2 minus tan squared theta over 2. Okay, so let's just go ahead and find a way to find out what the remaining volume would be. So you see in this structure, they have told us that this structure is made up of a hemisphere, right? And then this cone is drilled out of it. So the remaining volume would be everything else, okay, in that hemisphere, excluding that cone, the volume of that cone. Okay, so to find this, we're using volume because we're looking at the space filled up, okay, the remaining space. Do you say that if you say take the volume of the hemisphere and then you say minus the volume of the cone, okay, remove that, you'll be left with the outer parts. That's the remaining volume after that has been drilled into it. So let's go ahead and do that. So we need the volume of the hemisphere first. So to find the volume of the hemisphere, they've given us the volume of a sphere, it's 4 over 3 pi r to the power of 3. We need a hemisphere, which is half of this. So you can take the volume of a sphere. So to find the volume of a hemisphere, we will just take the volume of the sphere, which was 4 over 3 pi radius to the power of 3. And we're going to divide this by 2 or multiply it by half, because half of it would be a hemisphere. So this would be, if you multiply 4, we get 4 times 1 is 4, 3 times 2 is 6. And if you divide, that is just going to be, they both have a common factor of 2. So this is 2 over 3. Okay, so we get 2 over 3 pi radius cubed. Okay, so this is what we have. And now we're just going to take the volume of the hemisphere minus the volume of the cone. Okay, so the remaining volume would be found by saying, okay, so the volume that remains would be found by saying the volume of the hemisphere minus the volume of the cone. Okay, so that's what we're going to do. So this is equal to, the volume of the hemisphere is 2 over 3 pi r raised to the power of 3. The volume of the cone, as they have already given us, is 1 over 3 pi r squared times h. So 1 over 3 pi r squared multiplied by h. So let's go ahead and substitute. So this is going to be 2 over 3 pi, and then r, capital letter R, is, well, they didn't really ask us to, find that in terms of anything, and they didn't give us a numerical value. So as you can see, the final answer is also still in terms of that big letter R. So we leave it like that. And then minus 1 over 3 pi. Now, when we get to this little r, you see that in the previous question, we found that that is actually equal to capital letter R tan theta over 2. So in place of it, we're going to substitute that. And you can see that it's squared. So all raised to the power of 2 and then multiply by the height. Now, let's just see what the height of that cone is. Do you see that with this cone, the height of the cone is this? Okay, this is how high the cone is from that to there. And that is TV, which we were already told is R. Okay, so we know that that is equal to R. So we can just put that down. That is multiply by R. And all we have to do is simplify. Okay, so this is equal to still 2 over 3 pi R to the power of 3 minus, and we have here 1 over 3 pi. Now everything here gets squared. You have two values that are being multiplied. So R gets squared and becomes R to the power of 2. Multiply by, and you have tan squared theta over 2. And then multiply by R. You see that here in this term, okay, because terms are separated by plus or minus sign. So this is a separate term. That is a separate term. You can see that in this term, R and R would multiply. So this stays exactly the same. So pi R to the power of 3 minus, but over here, let's start with a number. We have 1 over 3 pi, and then R and R would multiply and become R raised to the power of 3. And then we just have tan squared theta over 2. Okay, so let's just compare it with what we have here. With what we have here, do you see how we have outside the bracket, they took pi out as a common factor? So we will do the same. So you see this pi, there's pi, that's what's common. So they just took common factors out. Okay, so we don't even have to look at that. Just take out your common factors. So in these two terms, what is common? We've got 1 over 3 common, okay, because this is 2 over 3, that's 1 over 3. So 1 over 3 is common in both of those. And then there's pi that is common, and then R to the power of 3. And that would be our common factor. So then what is left? If you look at this first term and you ask yourself, what do you multiply to this to get back to that? You look at the 1 over 3 and say, what times 1 over 3 gives me 2 over 3? Well, if you have 1 over 3 and you multiply it by 2, you get 2 over 3. So that is what is left there, 2. And then pi, multiply by 1 gets you back to pi. So we don't have to rewrite that. And R to the power 3, same story over there. And then we have in the second term, what do we multiply to get back to this? Do you see how they look identical except for this part? They just don't have that tan squared. So don't forget the negative. And then all you have to multiply is by tan squared theta over 2. And then that gets you back to this, okay? Because everything will just stay the same. So it multiplies and then just sticks together like that. And that is our answer. And that's really how they presented it as well. And that is it for this question. Moving on to the next question. Question 6.3 says, the cone is filled with wax and a wick. Okay, so with a wick, that is just that little string of cotton that you usually see in candles. You see that string that comes out of the candle. Okay, so what they're saying is the cone is filled with wax and a wick, and the wick is always 1 centimeter below the level of the wax. But the wick must not protrude over the level of the flat surface of the hemisphere. Okay, so we're going to actually need the image. I'm going to just go ahead and get this. And let's just go ahead and think about this. Okay, so here is our diagram and let's just read into this. Okay, so they say that this cone is filled with wax and a wick. And then the wick is 1 centimeter below the level of the wax. So if we had the wick, that string that will be there, and they're saying it's 1 centimeter below the wax, we need to know where exactly that wax is going to be. But then they say, but the wick must not protrude over the level of the flat surface of the hemisphere. So that wick, it shouldn't go over this flat surface. So look at what we can do with this. You see at T, we're going to see that as that is the top part of this shape, okay? That outer part of the surface. So this is below it, and then this is the actual limit, okay? We can't go beyond this. So it means that that wick should be 1 centimeter below this. It doesn't make logical sense to put the wick below the surface, because then it's not a candle anymore. Well, it's a candle with wax that you can't use because you're now going to have to dig in to find the wick to even light it. So I'm finding some issues with understanding this question. Maybe it's just because of how it was phrased. It seems like this is what they meant, because if they didn't mean this, it would be very meaningless for them to say everything that they're saying right now. Okay, mentioning that it should be 1 centimeter below the level of the wax. It wouldn't make any sense. So I think what they meant by this is that the wax, it's either that they meant the wax should be, so if we could change that word to wax, the wax is always 1 centimeter below the level of the wick. Okay, then that would make sense. Because what this means is, remember how they said, but the wick must not protrude over the level of the flat surface. So this line, this stick, this string of cotton, it can't go over that dot. So that dot marks the surface of that hemisphere and also the cone. It can't go over it. It must just be right there, right? Then it would mean that the wax is 1 centimeter below that wick. And then that would make more sense, thinking about what a candle is and them mentioning all of this. If not, the info wouldn't really need to be mentioned. Okay, so just to draw the level of that wax, let me just do that just so that it's just going to be, parallel to it. So we're going to pull that down and then I'll just look at it like this. So yeah, that would make sense. So the wax, this is where the wax starts. It's 1 centimeter below this. So if we went from the outer part, from the surface, and we went 1 centimeter down, we would just get the level of the wax. So just looking at this as this is the center of this, and then this is 1 centimeter down. Okay, so that would measure 1 centimeter down. And so we could just highlight all of that as well. Okay, so like that. So we can look at that as that is the wax, and it is 1 centimeter below the wick. Okay, and the wick cannot go over that surface. So I guess that's what they meant. Okay, so let's look at the info that they say. What is the question? They're saying the radius of the hemisphere R is 12 centimeters. Okay, so we now know that R is 12 centimeters and the angle of the cone theta is 36. Determine the volume of the wax that must be put into the candle holder. Okay, so that makes sense now. So the volume of the wax that must be put into the candle holder. Do you see that that is the blue part that we have? That would be really the volume of that wax. Not just the cone, but the volume of the wax itself. So how do we find the volume of the wax? Well, it's inside a cone. So if you know the volume of a cone, we can still find it. Remember, again, the volume of a cone is 1 over 3 pi r squared times h. But we need to take note of something. You see, when we say times h, we know that is the height of the cone. You can see that the height of the cone is TV, which is r. Okay, same thing as r, which is st. So that and that are exactly the same. But when we're looking at the volume of the wax, the height is different. If this is the wick, and we know that the volume of the cone or the wax filled inside, and we know that the wax filled inside the cone is 1 centimeter below that wick, then it means that it's 1 centimeter less than this height. So we knew that the height TV, right, R, is 12 centimeters. That would mean that this height that we are going to refer to is going to be 11 centimeters. Okay, and that's the only difference that we have here. So we will still say we need to find H and we also need to find R. Okay, they gave us big letter R, not small letter r. But here's the thing, you see that in the first question, we had this, okay? We said R is equal to big letter R tan theta over 2. So we'll go ahead and use this to find this small letter r. So R equals, big letter R is 12, and then we have tan 36 over 2. Okay, but then we're going to have to rethink this. You see, this can't be 12 anymore because we're not looking at the volume of just the cone. We're looking at the volume of the wax filled in the cone. So the radius of that, because that height is a centimeter less than what it used to be, we're going to have to use the height that we have here, which is 11. Okay, because with the cone, this was the circle, okay, on top. And you can see the radius. Now, with the volume of the wax, you can see this is the circle. Okay, because with the volume of the cone, this was the circle we had here. Look at the radius. And then with the volume of the wax, this is the circle we have here. And look at the radius. It's much smaller. Okay, so because of that 1 centimeter below. Okay, so that's what we have. And now we can finally find this volume. So volume equals, and we'll say 1 over 3, and we'll say pi, and then r raised to the power of 2. But that is 11 tan, and we have 36 over 2, which is really just 18, but that's fine. And then raised to the power of 2 multiplied by a height of 11 centimeters. And let's go ahead and substitute and find our answer. And this is our answer, 147.15 centimeters cubed, because this is volume. And that is our answer for this question. And that is it for question 6. Question 7 says, CD is a diameter and PC is a tangent to the circle. Chord DK is produced to P, and then PT intersects KC at Q, and then they give us the size of these angles. So CDP is 40 degrees. I guess we can also call that angle D really. And then they also tell us that DPT is 25 degrees and TQC is 65 degrees. Question 7.1 says, determine with reasons the size of the following, and we need to find the size of angle C2. Okay, so angle C2 is over here. Do you see how it's the angle between a tangent and a chord? So it's going to be equal to the angle at the circumference subtended by that same chord, meaning it is 40 degrees. Okay, so angle C2 is simply equal to 40 degrees, and the reason is because of the tan chord theorem. And that is our answer. Moving on to the next question. And then question 7.1.2, we need to find the size of angle K1. Okay, so just go to where it is. It is at the circumference, but you also see that it is subtended by a diameter. Okay, they told us that CD is a diameter. So it means that it is equal to 90 degrees. And that's because of the angle in a semicircle. So angle K1 equals 90 degrees, and its angle in a semicircle. And that is our answer. Moving on to the next question. Question 7.1.3 says we need to find the size of angle P1. So that is this angle over here. Angle P1. Okay, so look at how we can find this. I can see that they're using triangles here. So if you look at this triangle, extend this line, do you see how that 65 degrees is the exterior angle of this triangle? So the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So 40 degrees plus what gives you 65 degrees? That is plus 25 degrees. Okay, so we can go ahead and tell them that angle P1 is 25 degrees. And the reason is because we have the exterior angle of a triangle. Okay, and that is our answer. Moving on to the next question. Question 7.2, the last question for question 7 says, prove with reasons that TC is equal to QC. So let's just mark those lines they're referring to. So we need to prove that TC equals QC. Okay, so these two lines should be equal. You see, if you're trying to prove that two lines are equal, and you see that these two lines are part of a triangle, okay, what you can use is this. You see, if you have two lines equal, then it means that the angles opposite their equal sides are also equal. Likewise, if you have two angles being equal, it means the sides opposite those equal angles are also equal. And that's what we're going to work with here. So in this triangle, as you can see, because we need to prove that these two are equal, how about, because we can see that this angle 65 degrees, right? It lies right opposite TC. Then that would mean that angle T1, if T1, which lies right opposite QC, also happens to be 65 degrees, then it means that these two lines are therefore equal. Okay, so that's what we're going to do. Find angle T1. And how do we find that? Okay, we can find angle T1 using this larger triangle. See, look at this triangle over here. If you use that triangle, we can find it. We were already told that CP is a tangent, and we know that this is a diameter. So the diameter, okay, it passes the center of the circle. So remember that the radius, okay, because it comes from the center of the circle, right? It's always perpendicular to the tangent at the point of contact. That would also mean that the diameter would also be perpendicular to a tangent at the point of contact. That would really just be a theorem that comes from this radius being perpendicular to the tangent at the point of contact. Okay, so it's really like a corollary. So we can go ahead and use that. That's fine. So we can go ahead and tell them that we know that this angle over here is actually 90 degrees. Okay, so tell them that that angle is 90 degrees. That is angle DCP. So this is 90 degrees. So angle DCP is equal to 90 degrees because the diameter is perpendicular to the tangent at that point of contact. And then now that we know that that is 90 degrees, we can just use the sum of angles in a triangle to find angle T1. So angle T1 would be found by saying 180 degrees minus 25 degrees minus 90 degrees, and we'll find that. So finally, angle T1 is equal to 180 degrees minus 90 degrees minus 25 degrees. And our reason is the sum of angles in a triangle. And then 180 minus 90 is 90. And we know that 90 minus 25 degrees is indeed 65 degrees. And there we go. So because this is also 65 degrees, then we can see that we have two equal angles. Therefore, they lie opposite two equal lines. Okay, so let's go ahead and tell them, therefore, TC equals QC. Or we could just start by stating now that angle T1 is actually equal to angle Q. So we'll say, therefore, we know now that angle T1 and angle Q are equal. Well, I can't really call it angle Q. Let's just name it properly. It's angle TQC or CQT. Let's just call it TQC. TQC. We know that now. Okay, because they're both equal to 65 degrees. And now finally, we can tell them that these two lines are equal. So TC is therefore equal to QC. And the whole reason they are equal is because we have sides opposite equal angles that are equal. Okay, so not angles opposite equal sides, but the sides lie directly opposite equal angles. And that is our answer. And that is it for this question 7.2. And that is it for question 7. Question 8 says, in the diagram below, the points T, U, and V lie on the circumference of the circle with center O. Question 8.1 says, on the answer sheet B provided, prove the theorem which states that angle TOV is twice the size of angle TUV. Okay, so we are proving this theorem. So the first step to prove this theorem is to construct a radius. So we're going to join from U to O, but then we're just going to extend that. So you can extend it like creating a diameter, or you could just extend it to a point. That's fine. So we'll draw this and I'll just extend it to a point and I'll just call that point Q. Let's just call it P. It just looks too similar to O. Okay, and this is what we have. And so we have actually separated these angles into angle O1 and angle O2, and that is angle U1 and angle U2. Okay, and just ensure that you write down any constructions that you have made as well. Okay, so join UO produced to P, and now let's get proving. So with this theorem, what we're really using are these triangles. We're using this triangle first, and we're specifically going to use the exterior angle that we can see in this triangle. Remember that the exterior angle of a triangle is equal to the sum of the two opposite interior angles. So we'll start there by saying that angle O1 is equal to the sum of angle U1 plus angle T. So say angle U1 plus angle T. And the reason for this is because this is the exterior angle of a triangle. But here's the thing about these triangles. Do you see that in this triangle, we have from the center to the circumference, okay? That is a radius. And from the center again to the circumference, that's also a radius. We know that the radius is exactly the same, okay? All through. So because it goes from the center to the circumference. So these two lines are equal. We'll start off there. We can tell them that OT is equal to OU because these are equal radii. Now, if these two lines are equal, what it means is the angles opposite their equal sides are also equal. So this angle over here is equal to this angle. So we can go ahead and tell them that angle U1 is equal to angle T. Angle U1 equals angle T. And the reason for this is because we have angles opposite equal sides are equal. Okay, so with this, what we can actually do is update this equation, angle O1's equation. That would mean that angle O1 is actually equal to, we'll say angle U1 plus, but in place of angle T, because angle U1 and angle T are equal, we can replace that with angle U1 as well. And the reason we're going to focus on angle U1 is because do you see how this is part of what we need to prove? Angle TUV, okay, TUV is the sum of angle U1 and angle U2. So that's why we're focusing on angle U1. So that means in a nutshell that angle O1 is actually equal to twice the size of angle U1. And so we're done with that part. Now we're going to do the same thing really for this triangle that we see here, triangle VOU. You see that in this triangle, we have an exterior angle. And that exterior angle, angle O2, it is equal to the sum of the two opposite interior angles. So we can go ahead and start by saying angle O2 equals, and we'll add them, angle U2 plus angle V. So angle U2 plus angle V. And the reason for this is because we have the exterior angle of a triangle. Okay, and now we can also see that here we also have a radius. From the center to the circumference is the radius, center to the circumference. So those are equal radii that we have there. So we can go ahead and tell them that we can see that that line OV was equal to OU because they are equal radii. Now, because these lines are equal, what it means is the angles opposite their equal sides are also equal. So that means that angle U2 is equal to angle V. So we'll start by telling them and we'll focus on angle U2. So angle U2 equals angle V. And the reason for this is because we have angles opposite equal sides are equal. Okay. And now, because we know these two are equal, let's update this equation. So angle O2 is finally equal to, we'll say angle U2. And in place of angle V, just replace it with angle U2 since they're equal. So angle U2. And so finally, angle O2 is actually equal to 2 angle U2. So now we've got equations for angle O1 and angle O2. And look at what we can do with that. What they asked us to prove is that TOV, angle TOV, this angle at the center, is twice the size of that angle. Do you see that this angle at the center is made up by adding angle O1 and angle O2? So that's what we're going to do. We're going to add those angles. We'll tell them that angle O1 plus angle O2 is simply equal to, and let's just add what they're equal to. Angle O1 was finally equal to 2 angle U1, so 2 angle U1 plus angle O2 was equal to 2 angle U2. But we know that when we sum these angles up together, they give us the center angle, angle TOV. So we'll put that down. So this is actually angle TOV. And this is equal to 2. Do you see how 2 is common in these? So we can take 2 out as a common factor. And what are we left with? Angle U1 plus angle U2. And the reason we're taking that out is because we can actually add these together. When we add them, look at what they give us. Angle U1 plus angle U2 give us the angle TUV, which is what they were focused on here. So we'll say that this is TOV is equal to 2 TUV. And there we go. We have proven what they asked us to prove. And that is the proof. And that is it for 8.1. Moving on to the next question. Question 8.2 says, in the diagram below, the two equal circles with centers O and M are drawn. Okay, so they are equal, meaning their radius is exactly the same. Okay, so the same size really. These circles are the same size. Chords AB and DM are produced to C. So there we go, they produce to C. Chord OB is produced to meet AD at F. Okay, OB is produced to meet AD at F. And they also tell us that AB is a tangent to the circle with center M at B. And AD is a tangent at D, okay, to the same circle. And then the only angle that they give us is DOB, which is 2x. Okay, and question 8.2.1 says, provide a reason why DOBM is a rhombus. Okay, so let's highlight that. Okay, so You see, the thing about proving shapes like a rhombus, a square, a rectangle is before they can be those shapes, they have to be a parallelogram first. So this shape would have to be considered as a parallelogram before it can be classified as a rhombus. Okay, so looking at this shape, what we can do is this. You remember how they said that these circles, right, are equal? So we know that they are of the same size, meaning their radii will also be equal. So from this center to the circumference is exactly the same as from this center to the circumference. So we know that this is equal to this, which is equal to this, which is equal to that. Okay, all the sides are equal. But what I will focus on so that I can first say that it's a parallelogram before further proving it's a rhombus is I'll tell them that I can see that the opposite sides, okay, of this shape are equal. And now that I think about it, just because of how they phrase the question, they say provide a reason why it's a rhombus. So they don't really want us to like go into proving it. They just want you to provide a reason. So I'll go ahead and tell them that all the sides are equal, okay, because these circles are equal. So we know that all the radii are equal. So we'll say OB is actually equal to, I'm just putting these here, but then, we actually have, I won't say one reason, but we would have had one reason if they said that this shape was first a parallelogram, and then we had to further provide a reason why it's a rhombus. Okay, so all the radii are equal, and so that would conclude that it's a parallelogram. And so, okay, let me just conclude that first because we have the opposite sides of this shape being equal. And now that we know it's a parallelogram, we can further conclude that it is a rhombus. So finally, I'm just going to say that DOBM is a rhombus. And here's the thing. If you know that this is a parallelogram, for you to further prove that it's a rhombus, if you can show them that the two adjacent sides are equal, okay, one pair of adjacent sides are equal, then it is a rhombus. The second way to prove this after proving it's a parallelogram is that the diagonals of a rhombus actually bisect at 90 degrees. So 90 degrees and like that, okay? So we can just use this one because we can clearly see that. Okay, so finally we can just say it's a rhombus because you can see that OB is actually equal to MB. Because we can see that OB is equal to MB, and so that's because we have adjacent sides, okay? So one pair of adjacent sides are equal. It just has to be one pair. It doesn't really have to be two. Okay, and so this would be the main reason that they were referring to. But the thing is, for a rhombus to be a rhombus, it's first a parallelogram and then a rhombus. Okay, so that is our answer. Moving on to the next question. Question 8.2.2 says, provide the geometric reason why each of the following angles are equal to x. And the first one is angle A. So let's look at angle A. I don't really need these lines anymore. Angle A. Okay, that one is quite simple. You see how they usually have, okay, depending on what you have to prove. Do you see that we had to prove this theorem? Okay, the angle at the center is twice the size of the angle at the circumference. They're using the same theorem here. Okay, that's something you will notice and you should expect. So angle O, okay, or BOD is at the center and it's twice the size of the angle at the circumference. So this is x. So we can go ahead and tell them that this is actually equal to x. Angle A equals x. And the reason, we'll put that down. Okay, the angle at the center is twice the angle at the circumference. Okay, so that is our answer for angle A. Moving on to the next question. Okay, the next one is angle M2. So I noticed that I'm actually stating these things, but they didn't ask us to state this. They just want reasons. Okay, so they're already telling you these are equal to x. You just need to tell us why. Okay, so angle M2. Why is angle M2 equal to x? Angle M2 is over here. Okay, so if you look at this quad, okay, and it's really A, B, M, D. Do you see how it lies? Okay, each of the points, they lie on the circumference of this first circle. So it means that we have a cyclic quad here. And we know that in a cyclic quad, we have the exterior angle is equal to the opposite interior angle. So that's the reason why. So we can go ahead and say the reason this is equal to x is because we have the exterior angle of a cyclic quad being equal to the opposite interior angle. Of course, you don't have to write that in full. Okay, moving on to the next question. The next question is angle D1. So we need to find out why is that equal to x. Angle D1 is over here. why would that be equal to x? Okay, so this probably has to do with seeing how it's inside this rhombus. It probably has to do with the rhombus. We can think about how we can use this rhombus to find x. Okay, so here we go. Do you see these lines? Because this is a rhombus, it means that the opposite sides would be parallel, right? And so if the opposite sides are parallel already, then the reason this is equal to x is because we have corresponding angles. Okay, do you see how this creates an F? So we have corresponding angles on parallel lines are equal. So there we go. Angle D1 is equal to x because of corresponding angles on parallel lines. And then we can just state the lines that are parallel. That is DO and MB. Okay, so DO is parallel to MB. And that is our answer. Moving on to the next question. The next question, D, is we need to show them why angle B2 is equal to x. So angle B2. Okay, that has to do with, again, a rhombus. You can see that this is a rhombus, and in a rhombus, the opposite angles are equal. So we can go ahead and tell them that. Opposite angles in a rhombus are equal. So that is also equal to x. And there we go. Moving on to the next question. And question 8.2.3 says, now question 8.2.3 says, prove with reasons that angle D2 is equal to angle C. So show them why angle D2 is equal to angle C. Okay, so this seems like one of those questions where you're going to have to move from angle D2 and then find out what that's equal to and what that's equal to, and then it will eventually lead to angle C. And let's just see how much marks is this for. It's for 4 marks. So it's probably a 3 or 2-step process. Let's see how we can get to it. So you have a choice. You can either choose to start from angle D2 and eventually get to angle C, or start from angle C and eventually get to angle D2. So let's see. Angle D2, based on where it is, how can we move it? Okay, so based on where angle D2 is, I would have loved to use the tan chord theorem, but you can see the tan chord theorem is not going to work here at all. So you see that this AD is a tangent to this circle, right? And so, we would work with the angle between the tangent and the chord, but unfortunately, there is no angle at the circumference that is subtended by OD. Nothing, okay? Because then we have a rhombus here. So there is no triangle that was created. So we can't even deal with that. How about, so instead of doing that, once you see that this thing that is over here, it's not very easy to move it just because of how it has been drawn, what you can do is try to find it individually. So try to find angle D2 alone. So I'm looking at angle D2 and I'm just asking, how can I actually find this angle? So angle D2 can be found if we separately find it. And here's how we can find it. Look at this triangle over here. We have a triangle. O is the center of the circle, right? And O is going from the center to a chord. Okay, so to be able to do this, we would need to know what... Okay, I'm just realizing using this triangle is actually unnecessary. Look at what we can do. We can use this. So you see that in this circle, from the center to the circumference, this is a radius. And they already told us that this is a tangent. So we have the tan radius theorem going over here. So to find angle D2, if this adds up to 90 degrees, then angle D2 would be found by saying this entire angle, 90 degrees, minus x, okay, angle D1. And then that would be angle D2. So that's what we can just do there. So we'll find angle D2 separately and then find angle C separately. So angle D2 is equal to 90 degrees minus x, because we can see that the radius and the tangent are perpendicular at their point of contact. Okay. And now that we have that, let's find angle C. So angle C is over here. And just because of where it is, it would be best to use a triangle. So this triangle, not very helpful because I don't know what this is. And I don't really want to go through the whole process of trying to find it. So let's use this bigger triangle. Okay, there we go. So angle C would be found by using the sum of the angles in this triangle. We have a 90-degree angle. This entire thing is 90 degrees and we have x. So angle C is equal to, we'll say angle C to find this. You say 180 degrees minus that 90 degrees and then minus that x. And this is because of the sum of angles in a triangle. And so angle C is equal to 90 degrees minus x as well. And so you can see now that they are equal. There we go. So angle D2 is therefore equal to angle C. And there we go. Moving on to the next question. Question 8.2.4 says, prove with reasons that AB is equal to BC. And this is also for 4 marks. Okay, so AB equals BC. So that is this. We need to show that these are equal. Yeah, so from the way it's structured, you see when they say 2 lines are equal, you're usually hoping it's from a triangle, and this line is equal to this. So you can just show them, okay, if these 2 angles are equal, then those 2 lines are equal. But in this case, that is not the same scenario. Okay, we have 2 lines that lie on the same line, okay, the line AC, and we need to actually show that those are equal. So from the way this looks, it looks like they are using the midpoint theorem. Okay, so this is a theorem you learn in grade 10. And here's the thing about the midpoint theorem. For us to prove that these 2 are equal, and let me actually just put a little diagram of it here. With the midpoint theorem, this is what it states. It states that if you are given a triangle, let's call it ABC, and you are given this line, let's call that DE, okay? If you are told that AD is equal to DB and AE is equal to EC, then what we can conclude from this is that first, DE is parallel to BC, and also BC is twice the size of DE. Okay, so it's double the size of DE. So that would be the midpoint theorem. Now with the midpoint theorem comes its converse. Okay, its converse theorem. With its converse theorem, this is how it works. So it's kind of like an incomplete form of the midpoint theorem. With the converse theorem, what you are given is that you have one side, okay, you have this AD being equal to DB, and you're also told that DE is parallel to BC. Now, once you are given that, what you would have to conclude from this is that AE is now equal to EC, and BC is twice the size of DE. Okay, and that would be the converse of the midpoint theorem. So with this, if this is what we need to prove, we need to prove that these 2 are actually equal, then it clearly means that we're going to have to first show them for those 2 to be equal. Then all we need to have is if we can show them that AF is equal to FD, and at the same time, this line FB is parallel to DC, then it would conclude that AB is therefore equal to BC and that DC is twice the size of FB. Okay, so that's really what we're doing. We're not saying these are equal yet. We're saying we have to prove that. So let's find out why exactly. We can start with the easy part. Why are these 2 lines parallel? Well, because we have a rhombus. So we already know that FB is parallel to DM. And I'll just state that. Let's just say FB is parallel to DC already, and I'll just state that down. And we can just say, I won't say given, because the reason why it is because this shape is a rhombus. We didn't prove it was a rhombus. We just provided a reason why it was a rhombus. So I'll just say because it was already given that this shape, and let's just remember it was DOMB, is a rhombus. Okay, so I'm just putting that down. And now what we need to focus on is showing that these 2 are equal. AF is equal to FD. The only way AF can be equal to FD, if you're looking at this diagram, do you see how the line from the center of this circle over here, the line from the center of the circle, right? If it happened to be perpendicular to the chord, then it would mean that it would bisect the chord. So if OF was perpendicular to this line AD, then we would be able to conclude that AF is therefore equal to FD. So the next challenge is we need to show that OF is actually perpendicular to AD. So F1 and F2 are 90 degrees. How do we find that given everything we have? Okay, you see these lines are already parallel. We've stated that because we know, because of the way this shape is a rhombus. So that means that if you have parallel lines, corresponding angles on parallel lines are equal. So that means this is also 90 degrees because this is 90 degrees. So angle F2 is equal to 90 degrees because of corresponding angles. I mean, you could have also said angle F1 because of co-interior, but it doesn't matter. It's fine. So let's go ahead and say F2 is 90 degrees. Okay, corresponding angles and the lines that were parallel were, okay, those two lines. FB was parallel to DC. Okay, now that we have that, we can finally conclude that AF is going to be equal to FD. So the line drawn from the center of the circle, perpendicular to the chord, because we can see F2 is 90 degrees, okay? Perpendicular to the chord, what does that line do? It bisects the chord, okay? So bisects the chord. So that would conclude that AF is equal to FD. And we can say that AF equals FD. And our reason is that line from the center of the circle, okay, perpendicular to the chord. And now that we have that, here's where we prove this. We are not saying these two are equal yet. Okay, this is what we currently have. These two are equal and the lines are parallel. Therefore, using the converse of the midpoint theorem, it means that AB is now equal to BC, and we would just have to specifically tell them that the reason why is because of the converse of the midpoint theorem. Okay, so AB is finally equal to BC because of the converse of the midpoint theorem. Okay, and that is our answer. So you can see that those two are equal because we had this being equal to this and the lines being parallel. Therefore, AB is equal to BC, and additionally, DC is twice the size of FB, okay, using the converse of the midpoint theorem. So just make sure you know the difference between the midpoint theorem and its converse, and that should be fine. So that is it for question 8.2.4, and that is it for question 8. Okay, so that is the last question for this paper, and I hope to see you guys in the future videos.